Collisions. A series of 7 videos.
Video 0, Introduction. About collisions. Velocities. Momentum. Kinetic energy. When and why the conservation principles. Different reference frames, how, for what.
Video 1, The Bouncing Ball. Understanding conversions between the potential and kinetic mechanical forms of energy. Measuring the coefficient of restitution, E. Solving an apparent paradox.
With the ballistic pendulum, masses are very different and the collision is perfectly inelastic. As the two bodies share the same final velocity, the solution is easy to find. The mechanical efficiency of the collision depends on the relation between the masses of the two bodies. The interesting, and outdated, formula.
Video 3, Collisions 1D. Two equal masses. First, we will study the situation where one of the masses is stationary before an elastic collision. Then, we use relative velocities for when both masses are moving, before the elastic collision. At last, we learn how to use the coefficient of restitution to find the final velocities, after an inelastic collision.
Video 4, Collisions 1D. Different masses. Deducing, the hard way, the equations for the elastic collision, using, again, relative velocities. Discovering the mathematical usefulness of the coefficient of restitution.
Video 5, Billiards 2D. In billiards, the two masses are equal, one of the balls is not moving before collision and the collision is perfectly elastic. So, things are made easy and the math, although a bit tricky, is affordable. We enter the trigonometry world. It's the preferred situation for physics teachers around the globe. Video 6, Collisions 2D. The absolute general solution. Avoided or feared by many, the general 2D collision, any masses, any angle of collision, any velocities, any coefficient of restitution, is just another 1D collision along the line of collision. Forget the final formula, too long to remember. Just follow a few simple steps and you will master the, very easy, method. Collisions are everywhere. In chemistry, as bonds break or form.
In thermodynamics, as heat is transferred from hot to cold. A collision involves two bodies, A and B, in one system. During a collision, kinetic energy and momentum are transferred between the two bodies. After the collision, each body has a different velocity from that it had before. For after the collision, you should deduce the new, final, velocities of bodies A and B, V, A, F, and V, B, F. The system of the colliding bodies is a closed one. No flow of matter is allowed between the system and the outside. If you know M, A, and M, B, masses of bodies, A and B, before collision, you know them, after collision.
Velocities are vectorial, but, if we deal with just one axis, 1D problem, we trade with the vector as if it was scalar, a number. The value of the velocity is its x-coordinate, that is, its magnitude, with a positive or negative sign, before, according to the direction of the vector. What about when we solve a 2D collision? Then, velocities must be dealt as vectors. For each one, we must find its magnitude and direction. Besides the magnitude of the velocities, we will consider the angles they do with the x-axis. We have, on each axis, x and y, the respective components of the velocities. These components are, also, vectors but can be dealt as scalars.
The principles for a system which is closed, no mass to or from outside, and isolated, no energy to or from outside, are the conservation of the total momentum, always, conservation of the total kinetic energy, more or less. These two principles come as a set of equations, relating the masses and initial velocities of the two colliding bodies, with the final velocities of these bodies.
Momentum is a vector quantity. Kinetic energy is a scalar quantity. Why conservation of total momentum and total kinetic energy? If the system is isolated, both mass and energy are conserved. No force will be acted by the system onto the boundaries of the system, or by the boundaries onto the system. Internal forces do not count. Remember, forces come as pairs, action, reaction. If both forces are considered acting on the same system, they cancel each other. Two bodies, two systems. Two bodies, one system. Force F and force minus F, cancel. If interested, stop the video and read the proof for the conservation of momentum.
Please, solve this problem based on the conservation of momentum. You need to find the magnitude and direction of the final velocity of the red ball, the body B. Choose the positive direction, usually left to right. Call the equation for the conservation of P. Insert no values, care for the algebraic signal, masses are always positive. Got it? Note: F is a vector, F, V is a vector, V, P must be a vector, P, so, the equality holds for the coordinates in every of the three axes of space. This means that not only the magnitude of the total momentum of the system does not change, also its direction does not change.
If you are interested on the proof for the conservation of the total kinetic energy, EC, stop the video and read. If you are interested in how to deduce the formula for the kinetic energy, EC, stop the video and read. Kinetic energy can convert in other forms of energy. In any collision, a small or noticeable part of the kinetic energy transferred between the bodies that collide is converted into heat. So, instead of the above equation, we use the equation below. The value, E, is the coefficient of restitution. E equals 1, when kinetic energy is conserved, in its entirety.
Let's consider a situation where the two bodies have equal masses and kinetic energy is fully conserved. What will be the final velocities? The problem is much easier to solve when one of the bodies has zero initial velocity. After the collision, the moving body comes to rest and the second body goes away, with the same velocity as the other body, before the collision. The math demonstration is the easiest. Call for the two conservation equations. Since the two masses are equal and V initial B equals 0, we can greatly simplify the equations. What shall we do to combine the two equations of conservation, of momentum and of the kinetic energy? Square the first equation and subtract equations. VB final cannot be null. Otherwise, nothing would change, no collision at all. So V final must be null. If V final is null, then VB final must be equal to the initial velocity of body A. Now, these two bodies have equal masses, kinetic energy is fully conserved on collision, but neither of them have null initial velocity. We will solve the problem of finding the final velocities of these bodies, working with a moving reference frame where VB is 0. That is, a reference frame which follows the movement of body B, before the collision. We calculate the velocities, Vr, of the two bodies, in the moving reference frame where B was standing still. Subtract Vb from the given velocities, in order to find the relative velocities of the two bodies. We already dealt with the situation where one of the bodies is not moving, before collision. So, we can deduct, immediately, the relative final velocities of the two bodies. Now, we can revert velocities back to our absolute frame of reference, recalling the algebraic meaning of the relative velocities. The colliding bodies exchanged their velocities. This is a simple finding, much easier to disclose through the relative velocities trick.
Conservation of momentum does not depend on the reference frame. Stop the video if you are interested in the mathematical demonstration.
Conservation of kinetic energy does not depend on the reference frame. Stop the video if you care about the mathematical demonstration.
See you in the next video. The bouncing ball.